So hi and welcome back to the second part of the lecture. The main properties of unit impulse signals, as we said, first the sampling property, and we explained how it works in the previous part of the lecture. And the second property is the convolution. When you have any function 5t and you convolve it with delta t, you get basically the same function. So delta t is the only function that does not affect your signal when you convolve with it. Everybody knows convolution from signal and system previous course. Convolution is one of the most basic operations that we consider very fundamental in signal and system, and we use it in communication so frequently. And convolution is, we can find it and calculate it also by going to the frequency domain. We calculate the functions in the frequency domain, and then we multiply them with each other, we get the frequency response, and then we take the inverse Fourier transform of the output to get the output of the convolution. This is another way to solve the problem. Fourier transform of unit multiplication by a function, also we explained how it works. If you have 5t multiplied by delta t, you get phi 50. Fourier transform of unit impulse is constant 1 at all frequency. What does this mean by visualization? You have this in time domain, you have delta. If I tell you this delta function, draw it in frequency domain. Well, this is time. The x-axis here time, and the y-axis the amplitude. Now I'm telling you, draw it in frequency. This is frequency, and this is amplitude. Frequency, amplitude. What's the shape? Is this line, one line over all the frequencies. This x-axis frequencies. This is what it means. This line means this visualization. Clear? This is what I mean by translating your words or math to visualization. If you can do this for everything, you will be able to bring and come up with new ideas. You will be able to add new knowledge to this. But if you cannot link them, you are scared. You cannot think more beyond what's there in the literature. But once you understand these things and relate them to visualization, you will be genius, smart, clever, able to generate new ideas and come up with new solutions. And at the end of the day, you most probably you will be a researcher or inventor, patent inventor, producer. Those people who really deeply understand the things and the meaning of math and the meaning of word and how to relate them to physical parameters. Not focusing only on how to do that, but why and what's the effect of this on that, and what does this mean practically? Once you are able to answer this question, you will be able to innovate, invent, and come up with new ideas. This is the basic. So we try always to do this with any equation we face, with any sentence we read. Now, unit step function. We understood what's delta, its properties, how it affects the other function when it's convolved with them, when it's multiplied with them, and when you convert it to frequency domain. What about unit step function? Unit step function is the second most important function in signal and systems, and we frequently deal with it. And basically this is by math. By math, this is unit function. U of t, the signal, is equal to 1 when t greater than 0, which is this part, and 0 when when t less than 0, which is this part. So this is by equation, this is by visualization, and this is by word. When we say unit step, you must automatically understand in your mind this picture comes and this function relates to it. What's the relationship between unit step and unit impulse? Unit impulse delta t and unit step u of t. What's the relationship between them? U of t is the integration of delta t from minus infinity to certain time. If it is the integration, then delta t is the derivative of u of t. If I tell you, question, derive u of t, derive it. Yes, derive it. What's the derivative of 0? 0. What's the derivative of this 5? Derivative of a constant. What? What's the derivative of x? 1. What's the derivative of constant? Not exactly 0. It's delta. It's delta. This delta. That's why I tell you, u of t is the integration of delta. Delta is the derivative of this, u of t. Why? Why is that? If it is constant in math, they teach you the derivative of constant is 0. True? X plus 5, derive it. What's the derivative? 1. What's the derivative of 5? You considered it 0. Yes? If your constant is going from minus infinity to infinity, yes, that's true. Math is true. But if it is not going from infinity to minus infinity, there is discontinuity here. Yes, if there is jump here, discontinuity, it's not true. What you learned in math is not true. So the derivative of constant at a certain jump is delta. So the derivative of ut is delta t. Another thing, like when you say sinusoidal signal, this is sinusoidal signal. You draw it in frequency. In signal and system, you used to say that this is only delta at plus f and another delta at minus f, and this is the Fourier transform of sine. This is true only if your sinusoidal signal is going from minus infinity to infinity. But usually we don't have this in practice. We always limit sine within certain period. When you limit sine, the Fourier transform is sinc here and here sinc. Depends on how long the interval is, the sinc bandwidth will shrink. So there are some there are some rules that we learned in math or in signal and system, basic ones, and we just take them as hypothesis directly. When you see constant, put it 0. When you see function sine, put it delta, and that's it. But in communication, when you come to practical implementation, you don't have such a signal that comes from minus infinity to infinity. Can you allow your data to from minus infinity to infinity to transmit? When will your receiver receive the data then? Okay, in practice we don't have such thing. So math usually teaches you the theory, the perfect theory, the ideal conditions. But when you come to the practice, things become different, and you need to see the effect of these practical things on your theoretical knowledge and theoretical equations that you have learned. So basically now you know delta t, you know u of t, you know the relationship between them, and you know why the derivative of constant at certain jump is not anymore 0. Now, the sinc function, the third most important function we deal with in signal and communication. Sinc is defined as sine pi of t over pi of t. This is the one we used in signal and systems. But here in this course, we'll deal with this version of sinc, sinc t, no pi, which is sine t over t. The difference here, the difference between them, this one crosses 0 at pi, minus pi, 2 pi, minus 2 pi, 3 pi. But the previous one was crossing 0 at 1, 2, 3, 4, 5. You understand me? That's the difference. So basically, sync by t is equal to sync by t. This is the relationship between them. Let's see the drawing of sync. Yes, here this is sync. This is sync t. You have maximum value at 0, where you have 1, and then it crosses 0, the first 0 at pi, and the second 0 at 2 pi, and then 3 pi, and so on and so forth. This sync comes from what? This sync, suppose this is time domain, and I tell you what's the corresponding signal in frequency domain for sync. Rect square, yes. This is in frequency domain. When you have such thing in frequency domain, this is frequency. Then when you take the inverse Fourier transform, you get sync here. And if you have this in time, you get this in frequency. So interchangeable. Clear? A periodic signal. A signal is periodic if it satisfies this condition that we already explained. If G is periodic, its period is the smallest such t, and the signal repeats itself within this duration. Example, trigonometric functions are periodic. All trigonometric functions like sine, cosine, tan, they are periodic. Period of cosine t is 2 pi. Period of tan t is pi. Period of sine t is 2 pi. Yes? It repeats itself each 2 pi. Period of square wave sign sine 2 pi t is 1. So from the shape, when you draw the signal, if I give you any function like fx and tells you draw it, you just take values and connect them. From the shape, you know periodic or not. If G and F are periodic, their common period, least common multiplier of TGTF. This is to tell you if there are two signals that are periodic and you want to find the common period of them. This is by words. I know it might be difficult for you to understand it. That's why I will draw it for you. Let's say you have this signal. Yes? This is the signal, first signal. Yes, and you have another signal. Okay, this is the first signal, and you have another signal that's started from. So the first one has lower frequency, the second one has higher frequency. But at this point, both meet with each other. Yes? So if these two signals are summed with each other, what's the common frequency for them? The common frequency is the frequency of the higher one, conditioned on the fact that both start and finish at the same point. So they meet here. Suppose there are two signals. One is frequency of 2 and the other frequency of 5. When will they meet with each other? 2, 4, 6, 8, 10, and 5, 10. When they will meet at 10. Yes? So we consider this as the common period for them. Clear? Fourier series. Periodic signals can be written as the sum of sinusoids whose frequencies are integer multiple of the fundamental frequency. So what does this mean? If you have a periodic signal, any periodic signal in the world, you can represent it as sum of basis function, exponential basis function. And these exponential basis functions are related to sine and cosine. The most general representation uses complex exponential function. For example, g of t, assume g of t is periodic. Let's say sine or cosine. This signal can be written in this form: summation of Cn e to j 2 pi if not nt, from n equal minus infinity to infinity. Note the factor of 2 pi, since we are using frequency in cycles per second here in this case. Now what does this mean physically? If I have a signal, periodic signal, and I am representing it with different signals, what does this mean to you? I want you to understand the physical meaning of that. This means that any signal that's periodic, this signal is, think of it like cooked food, like ready meal. Yes? Give me example of a meal you like. Any meal. Any meal, you like or not, but it's a meal composed of many components. If I give you a meal to eat, food, can you tell me what are the ingredients of this food? Composed of what? Potato. For example, let's say I provide you with a sweet and I tell you, guess what are the components or ingredients of this halwa or sweet? Can you guess? It's very delicious, the food, after you cook it and make it sweet or prepare anything like that. It's very delicious. But it's basically made of eggs, oil, flour, jam, many other things. The same thing here with signal and systems. G of t is the cooked meal or the sweet you are going to eat. This is composed of so many things that are ingredients, pure things. You want to know these ingredients that when you mix them with each other, you get this G of t, the meal. This is basically what this equation means. You have something that on the front end, very nice, handy, and I like it. Its shape is very nice, its taste is very awesome. But what are the things that made this? So that you can make it frequently and start providing it for others, not only you don't eat it once. The same we are doing here. I give you a G of t signal that has beautiful characteristics, like it's periodic, it's limited within this frequency, has this property, has this property, has this property. But you don't know how to generate this signal, how to build this signal. Building it not by drawing it, building it by math. By knowing the functions that when you add them with each other, they bring you this signal. In this, you will learn how to analyze a signal to its ingredients, to its fundamental components. We call them basis functions. G of t, if it is periodic, can be represented in this form. Your goal is to find what's Cn, and when you find Cn's and how many terms, you sum them with each other and magic happens that you get G of t back. Fourier series coefficients Cn are complex numbers even when the signal is real valued. The Fourier series coefficient, how to find Cn, you take the integration of the multiplication between G of t and the exponential function. The integral is over any period of the signal. This is it. Sinusoids have finite number of terms. You know this Euler identity? It's very common in math. Any exponential function, e to j or e to it, can be represented or written as cosine t plus I sine t. Cosine t, therefore, can be represented in this form. Cosine t, the cosine t signal is basically the sum of two exponential basis function. Now let me tell you, if I come here, yes. Now let's be more serious. If I come here and remove this, yes, what do you see here? You see this, only this term. I tell you, suppose we have a cosine signal written as follows. Do you believe me? I'm saying this is cosine signal. Do you believe me? Before you take signal and system and assume you have basic math, tell you this is cosine signal. Usually I know cosine is this. How come you are telling me this is cosine signal? Yes, this is the cosine signal after you analyze it to its basis functions. After you know the ingredients of cosine, what makes cosine. So basically this is cosine. You can make a joke with your friend, the ones who are good in math. Is this cosine, yes or no? This one. And see how many of them they know that this is cosine. What's the difference? You wrote it in a different form. What's that different form? The basic form, the most fundamental basic form that produces your cosine signal. Now again here, remove sine of t here and tells you this. This is sine of t. Do you believe me? Yes, it's sine. How do you prove that? You go here, you go to this equation that any periodic signal g of t can be written as the sum of complex exponential basis function. Where is the exponential basis function here? This one, e to it, which is j, I is or j, the same. Plus, this is the first signal. Yes, e to it is the first signal, and e to minus it is the second signal. When you sum them together, you get cosine. Magic, yes? What are the coefficients Cn? If you apply the previous equation, you will find that C0 is 0, C1 is half, C minus 1 is half, too. So this is basically what cosine is. And sine of t, you have 0 at C0, and you have 1 over 2i at C1, and minus 1 over 2i at C minus 1. Now question that you might see in the test. Draw cosine in frequency domain, its amplitude and phase, and sine in frequency domain, its amplitude and phase. Yes? We know cosine t in time. We got the components that produces sine. These components are complex exponential basis function, basically related to frequency. How do you draw them? Yes, any idea? You have this. Let's say we want to draw cosine. You got here half. This is C1 half, and you write here half. C minus 1, this C minus 1 is another half, and C0 is 0. These are the coefficients of your expansion function. When you put them in the expansion function, you get cosine of t. The same with sine. What are the phases here? The phases 0, 0, which means 2 pi, 2 pi. But for sine, how do you draw sine? In amplitude is the same as this. But in phase, amplitude you draw like this. But in phase, you tell me at C1, what's the phase of C1? Minus I. What's minus I? What's minus I? Minus pi over 2. And here, I. What's I? Pi over 2. So you come here, this is pi over 2 plus, and this is minus pi over 2. This is how you draw it in frequency. the phase in frequency. So basically now you have an idea of how these are related to each other. Now give you an example at home, you can try this. W of t, if you have W of t rect, yes, and you want to find Cn. W of t is equal to 1 when magnitude of t between pi over 2, minus pi over 2 and pi over 2, and 0 otherwise. So Cn, from the definition, you take this from the definition. Fourier is the integration of the function y of t, w of t, the function w of t multiplied by exponential e to minus j and t. Now, one clever student has to be able to answer this. In the original definition function, I had e to minus j 2 by f naught n. Where is 2 by f naught here? Yes, anybody can answer this? Where is 2 by f naught? Why didn't I put it here? In the original function here, everybody remembers with me? Here, 2 by f naught, yes? 2 by f naught. Where is it here? I am now solving a real practical example that you might see in the test or the exam. Where is 2 by f naught? You tell me f naught is 1 over t naught. T naught is the duration, f naught is the frequency. What's t naught here? T naught is the period of the signal. What's the period of the signal? 2 pi. 2 pi multiplied by f naught, which is 1 over 2 pi, they cancel with each other. Clear? Everybody clear about this? And that's why you don't have 2 pi f naught. You have e to minus j and t. And the 2 pi, what's 2 pi here? T. This is t0, 1 over t, the duration. After that, you know integration. You know how to integrate and substitute. Once you derive this, you will prove by math that the Fourier, that the rect function, which is w of t, is basically the Fourier series coefficient of it are sinc, which can be drawn as follows. So once you have these coefficients, C's we call them, the complex coefficients, and put them with the exponentials, sum them together, you get rect. Clear? This is what Fourier series analysis is. And it's very important fundamental concept in signal and system communication and many other fields. And in next lecture, we'll continue talking about its features, properties, and the other related functions and problems related to it. And for now, we stop here and we continue in next lecture. Thank you very much for your attention.